Hi, I'm Coach Cowland, and in this presentation we're going to look at work, power, and energy. So before we begin, let's ask a couple of questions. So how would you define work? How would you define power? And how are power, work, and energy related? Have a think about those things before you move on to the next part. Pause the video if you need to. Are you ready? Okay. So work is about using energy to move something. There's a relationship here between work and motion. We'll talk about that in a minute. Um, And specifically, it's about moving something that is resisting moving, applying a force. So Newton's first law says an object at rest will remain at rest unless a force is applied to it. Well, here we have a direct tie with that, because unless you apply a force to it and put some energy into it, it's not going to start moving. We said that energy was about making a change, getting something to move, and we said that energy was about doing work to something, and here is the relationship between them. Now, when you do work, we've talked about the fact that there is a force involved. We've talked about the fact that there is a direction of motion, and those two must be the same. You can't, you don't do work on something if the force that you apply to it and the direction it moves are in opposite directions. So, for example, if you lift something up, you apply a force vertically upwards, and the displacement, the direction it's traveled, is vertically upwards, so that means you've done work on it. If you put something down, then the force that you've applied to it, well, the force that you're opposing is the force of gravity. So gravity is acting down. You're not actually applying a force, you're just letting gravity go. Um, so uh, so there's no force that you're applying, and the direction that it is going is down, which means that you're not actually doing work on something when you put something down. Even though they're in one dimension, the force and the direction are opposite, and that means that there's no work being done. So have a think about these. In which of the following situations is work being done? Pause the video, jot these down, give your answers, give a reason for why you think the answers are based on what we've talked about, and then move on when you're ready. Okay, let's move on. So, the relationship between work and mechanical energy. The forces and the distances tie into mechanics and kinematics, as we all know. And work is measured in joules, and we defined energy as the ability to do work. So there is a almost symbiotic relationship between work and energy. They are each other and they live for each other and they are part of each other. When you do work on a system, you give it energy. Energy is the ability to do work. Their definitions are tied into one another. So in one dimension, the equation for work is equal to force times displacement. So the force that you're opposing, or the force that you're applying, multiplied by the displacement, how far it travels. This is an equation you need to make a note of. And the units for this are joules. In two dimensions, the equation is a little bit more complex. This is more for physics than physical science. And here the equation is work is equal to Fx times cosine theta. Theta being the angle in between the displacement and the force. So if they are both aligned, the angle theta is equal to 0 and the cosine of 0 is 1. At that point, it just simplifies to work is equal to Fx. However, if the force applied is at any angle and there is an angular discrepancy between the force and the displacement, then the work done will obviously be less because the angle theta will be more than 0. And we'll look at an example of this in a minute. So, things to consider. If there's no displacement, then that work is 0. If the force and displacement are in the same direction, then the two-dimensional equation simplifies back to the one-dimensional equation, and W is equal to Fd. If the force and displacement are perpendicular to each other, then because the cosine of 90 is equal to 0, then the work will be equal to 0. This is the same as saying that if you slide something across a desk, the work done against the force of gravity is 0 because the displacement is horizontal and the force of gravity is vertical. Now you may be doing work against friction, but that's a different equation. So here's an example. A block is pushed with a constant force of 0.5 newtons in a horizontal direction. The block travels 1.5 meters. What is the work done on the block? Well, this is a very simple equation. 1.5 times 0.5 is 0.75 joules. So, the work done is 3/4 of a joule. The second example is a little bit more complicated. This time a block is pulled with a constant force of 2 newtons at an angle 30 degrees above the horizontal. The block travels 3 meters this time. What is the work done on the block? So when the block is traveling, the force is acting 2 newtons at an angle 30 degrees above the horizontal, but the block travels 3 meters to the horizontal. So the equation this time is 2 times 3 times cosine 30, and your answer here is 5.2 joules. Still reasonably straightforward. Now let's look at power. Power is a measure of how much work you are doing each second. It's a rate of work. In order to have any power to measure, you have to have done some work. Now if you do the same thing twice, once quickly and once slowly, the amount of work you do is the same because you're going to apply the same force and you're going to get the same distance. However, the amount of power you use is going to be different because in this case what's going to happen is that when you do something quickly, it's your rate of use of energy, which means you're using energy quicker. You put more power in for a shorter amount of time. So think about these statements and have a read of them and determine which ones do you think are which ones do you use the most power, which ones do you use the least power. Remember, power is a rate of work. Pause the video and then hit play when you're ready. Okay, you may be when you think about power, you may think of power in terms of electricity, and we certainly will use it for electricity when we get onto that section. So for example, power tells us how many joules of electricity are used every second in a light bulb, and various other things. Now this is going to come on to the section when we look at electricity and DC circuits. But right now we focus on power in terms of mechanical work. In the terms of mechanical work, the equation for power is work divided by time. However much work you do, divide by the time it takes you to do it. If we expand on this, and we know that work is equal to force times distance, then power is equal to force times distance divided by time. This last equation is for specific options. If the velocity is constant, if there is no acceleration, power can also be force times velocity. The work kinetic energy theorem is an interesting theorem and it's quite useful. We can see changes in kinetic energy, and from that change in kinetic energy we can work out how much work has been put into a system. So this equation is pretty straightforward. The work is equal to the final kinetic energy minus the initial kinetic energy, and that difference is how much more work has been put into a system or taken out of a system if the work is negative. Okay, thanks for watching.